Okay, good. All right, so so advanced engineering analysis, just to help you to appreciate what this is about. This is really a math course, not so much teaching you math procedures, but to some degree teaching you computer procedures. So now it's more, you should have a proper enough mathematical background so that you can use the computer because you understand the math that the computer is doing. So we're not going to be like undergraduate students who you have a question, you pull out a calculator and you don't do any thinking. It is quite common that you may have a little question like 100 minus 25, and I might say in class 75, and a student pull out the calculator. I say, sir, 75, sorry, you're right. You know, as though the computer should validate you, but actually you should validate the computer. So you should have an appreciation of the fundamentals, mathematical fundamentals, and so you appreciate what the computer is doing, and so you can do programming and such. Alright, so let's kind of appreciate why we do this course called engineering analysis. It really is a numerical methods course. And what is numerical methods? Let's go back to what engineering is about. Engineering is about manipulating, controlling, exploiting the natural world or the physical world. The physical world is run by laws, which pretty much is cause and effect relationships. What happens if if you have this reality and that reality, what is the outcome? Those are called laws. And if you are aware of laws, you're able to curb your actions or your activities to achieve a desired outcome. Right? And so designing in the physical world, designing physical systems or physical objects or things in order to achieve a certain outcome is what we call engineering. Okay? So I said this part already. So you're subject to physical laws and you're also subject to what they call mathematical laws, different from physical laws. And so the engineer looks at both the math and the physical world. There are other laws. Minister of Religion knows that there are spiritual laws too, just as valid or even more valid than the natural law or the physical law. But we are not considering such laws in this module. Alright? Okay, so these laws, we call them relationships. Alright? We just call them relationship. How, just like how one person and another person, a person is a system, you're another system. How we relate, there's a law of how we relate. And in physical systems, it's the same thing. And we call that relationship. We have different terms to describe the relationships. Alright, so you've heard the word function. It's a way you describe a relationship. A function is a parent-to-child relationship. For example, everybody here should know to use Excel. Okay? The function is called, let's say, cosine. So you write COS and you put something in the bracket. Alright? And let's say you put 10, no, not 10. Let's say you put 3 points. So let's say you put 3 in the bracket. Okay? Put cosine 3. 3 is actually a parent. And the answer is the child. Okay? because the three, the answer had no, couldn't bring himself into existence. He's dependent on the function and the three. So it's a parent-child relationship. Another way we express relationship is equations. And equations, you could say a function is an equation, but that's not necessarily the case. A function is how one thing comes from another. That's what we call a function. Okay? But the equation just really looks at two relationships, and it can go either way. That's an equation. Okay? And so it just looks at interdependency rather than dependency. A function looks at dependency, but the equation looks at interdependency. It's not saying one is more than the other. Then you have systems. Systems are multiple functions or multiple equations. So there are multiple dependencies going on, which causes the whole system to operate. So there's no one expression that defines the whole system. You can have several expressions. But this system is still a relationship. Okay? And so what the engineer is doing is you want to predict. The engineer is more concerned with prediction. But engineering principles can be used in understanding cause, not just prediction. Like forensics is still applying engineering principles, but instead of saying we are where we are now, where we will be later, you say we are here we are now, what caused us to come to this location. Right? That's kind of like forensics. And history, archaeology, all those things, they use the same principles oftentimes. So prediction or determine the cause of an outcome is what you call as an engineer solving a system, or solving an equation, or solving a function. Okay? You're trying to determine the cause or trying to determine the outcome. Okay? Okay. Now, there are ways in which we solve problems. We call them problems. Doesn't mean it's a negative thing. It's just a situation you're trying to understand. We call a problem. So there are a few ways we approach problems. First, we approach it analytically. Analytically tends to be symbolically. It's not necessarily numerically. That means not so much about numbers, but it's understanding the system from its characteristics. All right, its unique characteristics in the physical sense, physical world sense. And so you use expressions, symbols to help one understand certain types of systems or things or objects in the world. And you use algebra. I would say algebra, it goes all the way to calculus and differentials, and it's all still algebra. Use algebra to see those relationships. Okay? The other important skill is what we call numerical methods. Numerical methods now is used sometimes is a secondary step to the algebraic or the analytical. Numerical methods really is coming to a specific answer. So the analytical method is more curious about the relationship, while the numerical method is coming to a specific case or a specific answer that you want about your general relationship. Alright? So you can solve a system analytically, so your solution gives you an understanding of a general relationship. But now you have a specific case, and then your analytical method has to now revert or take a next step to become a numerical method. Alright? Sometimes, however, numerical methods can also give you an understanding of relationships. Okay, for example, a table of information, which is a lot of numbers, just one set of one little information. The temperature here in this room is 20 degrees or 25 degrees, 20 degrees Celsius. The pressure is, I'm a mechanical and chemical engineer, so pardon me using sometimes these examples. Alright. And the pressure is 100 kilopascals. Let's say something like that. That's just a specific case. Okay? But let's say I had several, what you could call those points. So I tell you that and I give you some other information. I say, and the temperature at another time is 30 and I give you a pressure. And the temperature another time is 40 and I give you another pressure. And you get all this information, then you start seeing a line. And that line now starts to give you a picture of a relationship. Alright? So numerical methods can also give relationships. Okay? A solution or solution methods are not strict. That's what we were just saying. They are really a combination. Alright? You need both methods to appreciate how a system behaves and predict an outcome or determine or estimate a cause. Okay, so there are some steps in I say solving numerical methods. Appreciate it involves, I just said, numerical method always, most of the time, starts out as a analytical method, right? Numbers themselves don't make sense in the physical world by themselves. So it's something that I have to be driving home to students when they give me an answer and they tell me a number. And I say, what's the answer? And they tell me a number. But they don't tell me a number of what. That's the issue. Because the physical world, numbers don't exist by themselves. They are applied to things. Right? So, yes, numerical methods, your computer doesn't understand the thing. Your computer just understands the number, but you have to appreciate you're talking about the thing. First, solving a numerical method problem, you must first interpret or review the problem. You're going to realize this is not very different from, for those who have done numerical research methods, or you've done design of experiments, or it's still the same general principles, but now we're applying to mathematics and engineering in terms of that analysis. Alright? But when you're doing a project, if you're doing language studies and you're doing some research, you still have to identify your problem and do some assessment of background and so forth. It's not any different for engineering. In those fields of study, there is relationships also. It's not physical relationships, it may be social relationships, other relationships. Engineering focuses on the physical world. Alright? And the science behind the physical world, we call it physics. Albeit you have chemistry and biology and all those things, those are still covered by physics or governed by physics. Alright? So you have to understand what you're talking about in the physical world. Then you have to next identify the models for that system. This is still analytical. So in all your various fields of study, there are some laws or sometimes it's laws and sometimes it is what we call accepted or conventional relationships. It may not be a law, but it's just a repeated behavior that is accepted as the way it goes. Okay? But these are models that are accepted out there. And so these expressions, these laws, are normally expressed in the form of algebraic expressions or equations. Maybe one, the problem may only apply one expression, or it may be several expressions. Algebraic, right? Or, for those who, I hope everybody at least touch a little calculus. You'll have to touch a little calculus in this course. Differential expressions. Differential expressions are usually relationships that have to do with how a system is impacted by the rate of change of another system. Okay? Alright? Some systems are impacted by the state, and some systems are impacted by the rate of change of the state. Alright? Those are differential systems. Some systems are impacted by one way you define the state of something is its size, and sometimes size is determined by summing, just adding things. But if you have something called a continuum means that the things you're adding are not, you can't identify them one, then the word summation becomes what you call integration. Okay? So that's summation is 1. So, for example, if I want to count the number of people in this room, I can count them 1. But if I'm going to do it on the globe, right? The number of people on the globe almost becomes a continuum. You get a map and you see a density of people, and then you move from summation to integration. Alright? There are also relationships that have to do with vectors and matrices. Means tabular and directional relationships. Okay? There are some systems that have to do with directions, and some systems that have to do with order of how the data is put together. Okay? A matrix is a table, a vector is a direction. Alright? Okay, so again, you have to interpret, you have to model. And interpretation, let me say this, let's say as an engineer you're given a problem. The person giving you the problem may not understand the physical reasons behind the system that they're asking you to assess. But you have to take it now to the next level. You have to ask additional questions next. So now you have the model, then you have to determine a strategy to solve. We're not saying you start applying, you have to choose a strategy. And when you choose the strategy or the method, because every problem, to get to the answer, you eventually have to start putting on numbers. Right? You eventually have to start pulling on numbers. And when you are pulling on those numbers, it's like using a calculator. You have to decide, if you have a long problem, you have to decide which part of the problem you're going to do first, which part to do second. Now when you take that information, you write the information down on the top corner of the leaf, and then you do the next part, and you cross out that, and then you take that information and put it together. That's still a strategy, right? It's a method. You're taking step at a time. So that's the manual way, just using a calculator. Can you see from where you are? Okay. So like use a calculator, you use manually, you store it in your head, or you take a piece of paper and you put information down. You can also do it automatically or automated, in an automated manner. Automated manner means, so the numerical method, which is now called a computer, does the storing and actually understands the sequence, just as the human would have done the sequence. So the human teaches the computer what is the proper sequence of doing something. Alright? This is what we call programming. Now programming is using computing for information and visualization. That's generally the IT or computing professionals role, but the engineer also uses the computer and does programming to model the physical world. Alright? And you have several levels of use of the computer. The first is the calculator. Alright? And then you can become a little bit, you have the general programming language, which is the same one that all computer scientists would use. And I'm a little backward, so there may be now newer ones. These are. And I was writing this, doing this slide or developing the model. These were kind of the Java would have been a more recent one, or Python. When I was in school, it was C. When I was just starting school a little later, it was C++. When I was a little boy, or just like in high school, it was something named BASIC. Alright, those are the languages. So that's general programming. Now, there's math programming. And math programming is really for engineers. And so you have MATLAB, that is the industry standard. So you will have to know MATLAB. If you don't know MATLAB, you have to learn MATLAB. That's not a prerequisite for the course, but you're going to get some exercises in that. Your first assignment on MATLAB is already on the website. I have to fix the due date. It's just an assignment, not asking you to solve anything. It's actually just asking you to type some things in MATLAB and see the answer. So you can start getting used to it. And there's also a basic quick guide to learning MATLAB on the website. Alright? Now MATLAB is the language, and it was developed by a company named MathWorks. But since then, there's another open source, no company, organization, Octave. Usually academics who do that. So companies make proprietary software, academics tend to make the free version. So there's something named Octave, which is exactly the same thing as MATLAB. It does the same thing. So I'm not permitted to tell you to steal software. You can download MATLAB. It's about 300 megs, big thing. Alright? When I was before MATLAB, there was something named Fortran. It still is around. These again are especially for math and engineering. Alright? Then you have another level of numerical analysis. It's starting, this one tends to actually be more symbolic. MathCAD, something called MathCAD. Alright? And there are some others here. Symbolic means you actually can write equations and the system understands your equation and solves your equation. Alright? And of course, very important numerical or software is called a spreadsheet. You have Excel, but then you have some others in LibreOffice or OpenOffice or StarOffice by another company, coming out of a company called Star Microsystems. Alright? So you formulate your sequence, determine how you're going to use whichever one of these tools, and you execute your sequence. Executing your sequence is an iterative process. You never get it, you rarely get it the first time. You do the method and it works to a certain extent and you don't know why it didn't work and you have to go back in and investigate. That's called debugging. If it gets to the end, that doesn't mean that your method works. So there's something called verification. Verification is to say, I got an answer. Does it mean it is the answer? Not necessarily. So you have to be wiser than the computer. Okay? To confirm, yes, that makes sense. Because the computer don't have sense. Well, Nowadays, they get in there. But the AI business. But so having verified, so debugging means you don't get to the answer, or you don't get an answer, and you have to keep reassessing why the sequence isn't coming to an end. That's debugging. But having come to the end, you must now confirm that it's not telling you a lie or such, and that's called verification. Last step, you have your answer, you know it's the answer. What does the answer mean? Okay, and that's called interpretation. Now what the answer means goes back to the original problem. By that I mean, if your company manager gave you a problem and you get an answer, he doesn't understand the answer of the computer. So now you have to retranslate it back to interpret what it means. Alright? So that's the whole procedure of the method, the numerical method. Okay? So we're going to go through about 5 different types of systems that you would solve in engineering, and we're going to learn not, you could go into a master's program and you just study one of these systems and you take all 5 modules just on this one system. But the goal, your goal is to just appreciate the system, know the tools to analyze the systems in a basic level, right? Or a little bit more than a basic level. First type of system is called the linear system. And I'm just going to show you some graphs. Remember, the graph represents what we call the relationship. Alright? If the relationship is written like this is called a function. But if it's not necessarily written like that, it's called a relation. Okay? Or I should say relation, an equation. The point is, we're not saying this is a child or that is a child. In this case, x is a parent, y is a child. Okay? The function sense. Okay, so what is a linear system? A linear system is one in which the quantity of one system or one thing to the other is proportional. Alright? If you double one, proportional and offset proportional. If you double one, you double the other. The amount you increase one by, you increase the other one proportionally by the same amount all the time. We call that a linear system. And we say system because it may be more than one relationship. Remember, we said you had equations, you had functions, and you had systems which are multiple equations or multiple functions. So in this case, you have one function here. Y is a function of x. Okay? That means x produces a child called y, and x also produces another child. Here we say the way it produces it is called a function. Okay? So this function is called f, this function is called g. Alright? Now, y is the child that we are producing. Okay? Now, if both of these are true, if this law is true and that law is true, you can't have two y's. So because you can't have two y's, you have to find where you have the same child, and that's called the solution. Alright? Did that make sense what I just said? Yes, sir. You can't have two y's because y is a child. Only one y, you have two functions, but you can only have one y. So where the two functions meet is the solution to that system. Father, mother. You can have more than two. You can have several. But the point is, the solution is where they all agree. They don't all agree, you don't have a solution. That's how the world go. Yeah, man. How can two work together unless they agree? Alright. That's right. Amen, sir. The next type of problem that we look at is called the root finding problem. Or sometimes you can call it the nonlinear problem. The nonlinear problem. Okay? It's a relationship that is not proportional. The nonlinear problem is usually expressed in which you try to find where the system equals 0. It's not that 0 is the answer you want, but you're going to rephrase that or repackage that relationship so that you can express it, so that you need to know when something in that system is 0. So we call that root finding. But there are other, I don't want you to be stuck with it being a 0 issue. It's not about a 0 issue. It's really about non-linear systems and solving non-linear systems. That's what this is about. Alright? Something about non-linear systems is different from linear systems. Non-linear systems may have several answers. Even if it's just one or two relationships. There are two relationships here. The first relationship is y equals 0. That's one of the functions. And the other function is y is this. Okay? So what we did is we had two relationships and we repackaged them so that one of the relationships is y equals 0 and the other relationship is this. Now where they meet is the answer. Okay? If you have a linear problem, you can only have one answer because two relationships. But when you have a nonlinear problem, you can have more than one answer, even if it's just two relationships. Alright? The next type of problem is called the optimization problem. Optimization problem usually asks what is the best or the worst, or the least, or best or worst, or least or most. Okay? Generally. And that's a type of problem you have in engineering, right? Maximize profits or minimize losses or minimize costs or such. So again, there are strategies for solving the problem of optimization. Now, of course, optimization can be a linear issue or it can be a non-linear type of relationship. Next type of problem or situation, we call it interpolation. Recall that I said that information can be given as functions, as equations, pardon me. And I said, but you could also have it given as sets of numerical information. If the numerical information is known, you can approximate the relationship. The dashed line represents the approximation of the relationship. We don't know definitely that this is what the function is between. We know these points definitely, but you can use that information to assess what's happening where you do not have the information. That's called interpolation. Alright? Everybody should generally know to do what's called linear interpolation. It's a basic type, but you have also these types of interpolation called nonlinear interpolation. Alright? So we'll learn about that. Now there's one in which I will not do, but I include it here. And I think in a future course I may start including it because not everybody does design of experiments. But note, when you run an experiment, your experiment gives you an outcome. If you repeat the experiment, it likely will not give you back exactly the same thing. Right? Hello?
Yes,
I just want to know that here with me. So the function is no longer certain points, certain add points. Your function is now based on a general range of information, and it's less certain than the interpolation case. We call that regression. Alright? Call that regression. It is to estimate the behavior of something based on experimental information. Interpolation is to estimate the behavior of something based on certain information or sure information. Alright? You should do it in design of experiments. Right?
That's why we're not doing it in this course.
Right.
Alright.
And this is more important, especially for research students, because they're doing experiments. Alright? But in your companies, if you're at a level where you have to do research in your companies, then such things would apply also. Alright, so that's regression. Next is something called integration, numerical integration. Again, what you have is these points, and so now there's a host of other information that you can get just from points. It is not just the answer of the points or information close to the point, but other information. And I just spoke about something called integration, which is how to sum up things. And remember I talked about the differential or the derivative differential equation, which is the rate of how something changes, and that might be important to understanding a system. So the points themselves is not rates, but by looking at the points you should be able to assess rates. Alright? We call that numerical differentiation. And we'll touch on this, which is still related to numerical differentiation. It's called solving initial value problems and partial differential equation. What's an initial value problem? An initial value problem is one in which you have a certain information, you know a relationship, and from that you can assess what will happen. Usually, time is the period, right? So at a certain time, what is the outcome? Okay? At a certain time, what is the outcome? And so they call it initial value problem because it's usually a time-based assessment. And you have something called boundary value problems. That's one in which you know what's happening at the outside of a system. Okay? It's called the boundary. And you know about the relationship, a differential equation again, that expresses how everything inside should relate to each other. And based on that, you can say what is happening at a certain location. That's called boundary value problems. Okay? So, generally, this is what you're going to be doing for those types of problems, excluding. I probably won't give you partial differential equations. Things like the differential equation module, something like that stands by itself as a module. I wouldn't do it justice even doing much more than introducing that to you. Everybody has done in terms of using numerical methods. Alright? But you'll appreciate how you can use numerical methods even with integration and differentiation and such. Alright? So this is how we pretty much will go through each module. I kind of give a scenario of a normal engineering real world case. Go to explain the methodology or methodologies. There are more than one methodologies for each type of problem. Linear systems has several methodologies. Root finding has several methodologies, and so on. Alright? And I'll work out some examples, or we will work through some examples. You'll get some, you'll see how you can modify the solution or different type of methodologies for different types of systems. And you are going to have to do some working out of a more detailed case. And each time we meet, I'll sort of go through our assignments, see what you do, correct some if there's some misunderstandings and such. Alright? Now, before we leave, let's talk about the project or the projects. Not yet, what I'm going to say to you is not yet on the system or on the website, but for those who came in after, let's go back to that. So what we have here is where you're going to get your information. I'm just realizing that the recorder isn't recording the whole thing. You realize? This is where it's recording, but that's fine. So go to this website, please. You're going to register. It's like registering into a university. Just register on the website, then you enroll in the course. You're going to look for ENG5000. Enroll. To enroll, you're going to need a password. They call it a key. The key is Newton. Why Newton? You're going to appreciate this man named Newton. He is in every single thing. So he's actually big in maths too. And so half of the engineering methods, Newton deal with those two. Same as that. Remember that. As great as he is, he's still dead here. As great as he is, he's still dead. Remember that.
That's a good one.
That's a good point.
I was thinking about when I saw it for.
Alright, so Newton, so the password is Newton, alright? Okay, so here we have two projects. So go to the website, passkey is Newton, and there you'll see everything related to the module. I will also, on that website I will post specific requirements of the projects. The first, let's go back to the website now. The test will be a written in class test. It's just your demonstration of your understanding of. I'm going to shrink this so I can stay within the recording window. Alright, so here's the website. So let's go back to the groups. So here are your groups. So here's what is going on. Two already sign up. Alright. So here's the purpose of the groups. The project is going to involve, the first project is simply this. You're going to do an assessment, a literature study on computational tools that are used in these fields of study. That's more project one. Okay, the whole span of it. Then identifying and appreciating how this tool or software, what its unique strengths based on person's review of the material. Where it may be applied. So electrical circuits is a broad thing, so you could talk about different tools used, electrical or numerical methods, electrical tools, not electrical, computational tools that are used in analyzing such systems, and you have different types of electrical systems or problems or that somebody may want to analyze. So you break it down, give a more robust explanation of that. You will include both proprietary and what's called open source software in your analysis. Okay? That's generally project 1.
Hold on. This is a study on computational tools.
Yeah, numerical and computational tools, software that are used in these fields of studies, whichever one you pick. Alright? It's a report. It's a report on those. Resist the temptation to just do a web search and cut and paste. I don't want to say resist, just don't do it.
How much?
All of that will be.
How big should this project be?
Yeah, man. All of that will be. All of that I'll say. I'll post that, but I'm giving you an understanding of what the projects are. All right. All right. The second no, that's the first project. That's what we do about midway through the period. More toward about start of November or so. All right. The second project is you will, and it also, the second one now involves a presentation in which you have to identify the primary open source software used in whichever field of study you want to choose. Alright? You are going to, usually every software has what they call demos. That means a very simple problem in which they show how the software can be used to solve that simple problem. Make sense? So you could pick a demo, no problem, but you have to demonstrate the use of the software. One, and you're going to do a presentation on the software and its features to the class. And two, you are going to use MATLAB for the exact same problem that the software was solving. You are going to have to build a computational code to do the same thing. Remember I said the simplest, remember I said it's the simplest, the demos are always a very simple case. You understand what I'm saying? Demo is a simple case that you're solving. So let's say you're in urban transportation and urban planning, you're doing a transportation problem. And transportation problem have to do with vehicles, and then say you just plug in some simple information in the software package and bam, you get the answer. What you will do now is you're going to write a MATLAB code or Octave code, and you now will have to get the same output that the software would have given you. What's the purpose of this? The purpose is to show you, because it's not for everything. You can find a software package to do it.
So basically we're creating a program that's supposed to complete the activity that was done by the software.
Right. But understand this, you're doing the program, so you're going to do a very simple version, because you're just doing the program for that problem. You're not going to do a program. The software is made for a host of different types of problems. Okay? But your code is going to be tailored to a simple problem that the same software would have solved. And your solution must be the same as the software solution. Yes?
This is why it's open source.
Yes.
What if in the open source software, on top of the basic principles they use, basic engineering principles, they have some tweaks to them add, like just for that software?
Alright, so yeah, so you said that's probably why I said open source. First of all, open source, everything in terms of the engineering Not in terms of, it may be some comp-sci brains who develop some of these open source. So there may be some computing things that are special that you may not understand, but they can't go beyond what the basic engineering principles are. It's the same engineering principles of your respective fields of studies, right? And so they apply the same rules that you would apply. There's nothing interesting or new in that information. Alright? Understand what I'm saying?
Yes.
Okay. So that will be the second project. Pardon me? Yeah, man. But you can't get to the. Yeah, I want you to learn. You know, just get your mind a little. And of course, I'm telling you from now because you would start the second project from now also. But the point is, it's like really one project, but midway you're going to present on your progress in understanding the software and how this software is unique from the other software out there. So it's really one project, but you're presenting it in two parts. The first part is not really so much concerned with your specific software or case. It's more general, and so the second half of the semester now, or the period, will now focus on a special case. That's all. Alright, the first one is just a report. The second will be presentation of the report. Or you're really going to present a problem, present a problem, present the methodology of solving the problem. Remember, we just went through some steps. You present the methodology. So that will be done as a report and as a presentation. And then you do a demo. So you come, you do the demo. The demo will show the open source package doing the same problem and you doing the same problem. And note, you are not asked to make yours look like theirs. What's called a graphical user interface. That is not a part of the assessment. You're not being asked to make yours look like theirs. It's the information, it's the solution that is the important thing. Alright? Yeah?
The demo, it going to be like a 2D or a 3D demo.
Anything you want it to be.
So wait, that's what I have to say. What if the open source software? So for example, I want to analyze. If I have a step file or something, then run the analysis on it. So wait, how would I get the step file on my file? I can't see it. I got a part. That can't be part of it. What part of the project?
I'll give you a broad enough topic that you can pick something that you can handle. Alright?
You know what I mean, sir?
I know what you mean. But structural analysis, you'll probably have to do a little research into really what goes into it's really something called finite element methods, right? Which is still numerical analysis, and the principles you learn in this course actually will go into that. Finite element methods. Alright, so that's really what is the project. I'm telling you from now so you can kind of get started.
So I want to it's a demo. Alright.
So demo means, to make it easy for you, every software always comes with demos, which is a simple case of how you apply the software to solve something. So I'm saying, using one of their demos, or you can make up your own demo, make up a simple case and apply it using their software, and then you're going to write a code imagining somebody needs to get a solution to a problem. They don't have the software that is out there, so you make a software where a user is going to be asked to put in some information. Not you, you know, you're making the software that you can give to somebody.
Well, there's never part I wanted to know about. So look at another software that exists.
Right.
Okay.
You look at a software that exists, but make sure it's an open source software. I also mentioned open source. It's a little exercise everybody must know. You see, when you go in your fields, you tend to be told by the people out there that this is the software you have to use. So you need to do your own studies and realize there are a lot of ways to get into the answer. And you'll also need to learn that sometimes you may have a problem that it don't make sense trying to find a software. You may never find a software, but if you are an engineer and you know numerical methods, you can get to the answer. That's what this exercise is about, because that's the goal of the course. Alright? Okay. That's it for the evening. I will try and keep our sessions to 2 hours. I know I went over the 2. This is more an introductory session. I'll try and keep it to 2 hours. Alright, let me stop the recording and then. So what I'll do is, hopefully by Monday or Tuesday of the following week, you'll see a flash video of this session on the website.
Oh, great.
Alright? You see it? Hold on, let me stop recording.
Let's go.